So in Gauss theorem, before going to the Gauss theorem, we'll need to have a background on flux, on electric flux. So we'll first study that as an electric flux. So electric field lines, as I have said, they are like a flow. That is, something is flowing. When something is flowing from the positive charge to the negative charge, or something is originating from the positive charge. It's like something is flowing out from a positive charge. It's not a line, it's a flow from which it originates from the positive charge, and the flow terminates at the negative charge. That is all we know about it. And after we understand how electric field lines are generated, we can just work with electric field to study the behavior of electric fields. As in, if suppose I have electric field lines like this, by studying the properties of this electric field, I can tell the properties of charges which created this field. And that is what we are going to do here. So electric flux, before defining electric flux, we have to define several other things. So electric flux basically measures the amount of flow through an area, the amount of flow that will through an area. This is a hypothetical area, and through this area, electric field is flowing. So electric flux will measure how much amount of electric field lines they flow through it. To define it, I will write electric flux is a measure of the number of lines of forces. I have told you the greater the number of lines of forces, the stronger is the electric field. So it's a measure of the number of lines of force. Passing through a surface held in the electric field. That's the definition. And I'll first give a basic definition. For example, flux in a uniform electric field. Now, a uniform electric field does not vary. It's easier to calculate flux in these situations. And draw the field lines as horizontal. So let us say you have an area like this. So see, if you have an area like this, just call it A. I'm not going to say that this is a circle or something. It's a circular area, and the area is perpendicular to the field lines. Okay? Area is perpendicular to field lines. The electric field line is, magnitude is E, and its area is A. So simply we write the phi. Phi is electric flux. Phi is the value of electric flux. We simply write it as E into the area. As simple as that. Just multiplying the uniform electric field with the area. Now this holds only when area is perpendicular to field lines. Area is perpendicular to field lines. Any questions up to here? I know we are just building up the concept, so it will still take some time before this your mind grasps these concepts, but believe me, you'll soon get used to it. So through this circle, this many amount of electric field is passing. So flux is electric field into area, as simple as that. So if this has example 1, I'll also take example 2. Let us say my electric field line is like this. And my area is not perpendicular. It's, let us take it as not perpendicular, but something like this. I want to draw a circle, but standard is okay. So here my area is like this. You know, if I directly multiply the electric field with area, then it will not give me the right answer, because the area is greater than this area, right? This area is greater than this area. So what I do, I will just take component of this area in the flow direction. I will take component of the area in the flow direction. Let us say angle between the original diameter and the projected diameter, this angle is theta. This angle is theta. So if you write phi, instead of multiplying this with total area A, you will write the projected area. What is projected area? Projected area is A cos theta. So your flux will be EA into cos theta. That will be the amount of flux. All right. That will be AE into A cos theta. Now we don't want this this idea of taking concept of taking the projection of area is simplified by another concept, by defining the area vector. By defining the area vector. So what is area vector? Area vector has magnitude equal to the area of surface, and its direction is perpendicular to the area. Perpendicular to the area. For example, if I have this is my area, call it pi r square or just A, then area vector will be perpendicular to the surface, like this. This is your area vector. You can write area vector as, if this is a circle and area is pi r square, you can write this as pi r square and direction is I cap. Suppose you have a square plate or rectangular plate, and this is like this. The length is L, the breadth is B. Then area vector will be perpendicular to the area. So area vector you can write here as L into B, and it is upward, so J cap. Just like this. So even if you go for the first case, we see the direction of area vector is like this. So we could have written flux as, yeah, the definition of flux won't change here. It is just E into A. But here see, area vector was earlier in this direction, and the angle with the electric field that area vector makes is theta. So you're taking component of a vector, that will be a cos theta. So we have a new definition for flux. We can just write it as E vector dot A vector, because dot product gives you the cos theta. So flux is E dot A. Here also you could have written flux as E dot A. That would have given you EA cos theta, but theta is 0 degree. So EA cos 0 degree, that would give you E times A. But here EA cos theta or E dot A, where A vector is an area vector defined as, it has property which is whose magnitude is equal to the area of surface and its direction is perpendicular to the area. So you can calculate flux through a uniform electric field through any area. Okay, are there questions? So I'll give you some basic problems on calculating flux then. Now this is a square in YZ plane. The dimensions are A, and the field is in the X direction. The X direction. Value of field is E. Okay. Find flux through this surface. Flux through this rectangle, a square. This is the electric field line. Solve it and tell me the value.
Sir, E vector A square.
E vector is along the x-axis. You can write this as E naught I cap, and area vector, as we said, is A square into I cap. So flux will be E dot A. That is E naught into A square. Correct.
Sir, is it important to write I cap?
If you write it, then your answer is complete. Here we are solving from the basics. So I'm writing it to explain basically. But in exam, it's better if you write it. If it's a 2-mark question, then better write it. Next question. Suppose there is a circle.
Could you please go back to the previous question?
This radius is R. This is normal to the circle, and electric field is like this. This is the direction of electric field. Value is E, and this angle is 60 degrees. find the value of flux. This is a circle. Rishit, can you tell me the value of flux here?
E pi r square.
E pi r square. But see, they are making angle 60 degree, na? Will
Then
be E
cos,
into,
cos 60.
yeah, cos 60. What's the value of cos 60?
Uh, root 3 by 2.
No, that's not the answer. You have to revise trigonometry. Cos 60 is 1 by 2. So answer will be E pi r square by 2. Suppose, just one more problem. This is a rectangle. Side is 10 centimeter. This side is 50 centimeter. And electric field lines are horizontal. Value is, call it 10 to the power minus 3 Newton per Coulomb. And the angle between this two, this is given as, this angle is given as 30 degree. Then find the flux. Find flux.
Sir, we will have to convert centimeter into meter.
Yes.
The value of cos 30 is root 3 by 2, right?
Yeah. If your answer has root 3 in it, then your answer is wrong. Although cos 30 is root 3 by 2. So any other answer in which root 3 is not coming?
5 into 10 raised to minus 5.
5 into 10 raised to minus 5. Okay. What, can you explain the solution? Electric field is 10 raised to minus 3. Yeah.
Area into electric field.
But your answer is matlab your answer should be E into A into cos theta.
But E is along the x-axis, so cos.
But what is the direction of area vector?
Uh,
See, as I said, from the definition, the direction of area vector is perpendicular to the area. Right? Here, see, area vector has magnitude equal to the area of surface and its direction is perpendicular to the area. I was always drawing area perpendicular to this original area. Area vector was perpendicular to this original area. So what is theta? Theta is angle between E and A, not E and the surface. So this is what you should take as theta. Theta is angle between E vector and A vector. Theta is not the angle between E vector and the surface. So if this is 30 degree, then your theta will be 60 degree. Calculate the correct answer now.
Sir, how theta is 60 degree?
Because this E vector is perpendicular to A vector. Means this surface, the area vector is perpendicular to the surface. So this angle is 90 degree. This is given 30. So the remaining should be 60.
60.
Calculate the value of phi. Apurv, what is the answer now?
Sir, 0.0025 into 10 raised to minus 3.
Okay, if I like to write it in scientific form, I write it like this: 2.5 into 10 raised to minus 5.
Yes, yes, sir.
Yeah. The scientific form is the first number should be between 1 and 10.
Yes.
It should be greater than 1 and less than 10. That is called the scientific form. All right. So this is the flux when electric field is constant or electric field is uniform. But what happens when electric field is non-uniform? How to calculate area then? How to calculate flux then? We'll take another piece. Electric flux for non-uniform fields. So non-uniform fields, they can be like anything, any shape, any variation could be like anything. And if you're having non-uniform fields, E is varying, E is not constant. The value of E at each and every point will be different. So if I draw an area, even I can take area like anything. I can take area like a curvature, not only a particular area. So here, what we would like to do is divide this area into very small segments, very small segments. and there will be a point where this field would be crossing it. If I zoom this out, it will look like this. This is my very small area, so I'll write it as dA vector. And let us say electric field through this small area is E vector at that point. So I can calculate the flux through this small region. The flux through this small region can be simply written as d phi. That will be E vector dot dA vector. No problem with that. I've taken a very small area in a very small region. For that small region, I can take my electric field to be constant. Even if it is varying continuously for large distances, for very small distances, very, very small, dA is called infinitesimal area, means very, very small area. For that small area, the electric field vector can be taken as constant. For infinitesimal area, electric field could be taken as constant.
Sir, here we don't have to take the angle between vector E and surface.
When I write dot product, an angle is already taken. What is E dot dA? That is E dA cos theta. Right? Here I am writing vectors, not just E and A. Is that clear?
Yes.
Okay. Now, if you want to calculate total flux through this region, total flux through area A. Now, area A has a random shape. It is not a very good shape, but luckily we have a tool in hand that is called integration, and we can calculate total flux through this area by integrating this value E dot dA. What integrating means is that you're basically adding up fluxes through all the regions, through all these small regions, through all these small dAs. And if you add up all those small flows, all those small E into dA, what you will get is this value phi. For these type of shapes, for non-uniform fields, for random areas, for distributed areas, for different types of areas, you can just write phi is equal to integration of E dot dA. That is called the electric flux. This is your electric flux.
Sir, A is circle.
A is not a circle. It's a random shape. It's not a circle. It's just a bent out area. That's why this is the most general formula. A is not a circle. Any questions? Shall we move ahead?
Yes.
Okay. After defining electric flux through a surface, I can also define next as electric flux through a closed volume. electric flux through a closed volume. So again, I have my electric fields. And suppose they are like this, or any random electric field is there. And I would like to take my shape as a volume. Means, I hope you can imagine this. This is like call it a cashew nut shape. I just want to give it a random shape. So imagine it, that's the cashew nut, a big cashew nut. And you have a shape like this. Now, what we can do, this is a closed volume. But even a closed volume is made up of areas. Means every volume has a surface area. If it is a closed volume, it has a surface area. And at each and every point, you can draw small surfaces. Means at some region, flux will be entering, and at some region, flux will be exiting. At some region, flux will be entering, at some region, flux will be exiting. Let's say flux is entering here, exiting here. So all this red portion are the points where flux is entering. And this red portion are the points where flux is going out. So here, we can again find the value of total flux through this volume, the electric flux, as summation of E dot dA over the full volume. Summation of flux E dot dA over the full volume. But since this is a closed volume, it is a closed volume. The volume is not open. The area is closed. So we like to write a dot, or like to make a circle in the integral sign. That's all we have changed. The notation has changed. The circle represents a closed volume. This is integration through a closed volume.
Integration through a closed volume.
Yeah, closed volume. Or you can say a closed surface. A closed surface is a volume. If you want to write the unit of flux, it will be Newton per coulomb into meter square. That will be Newton into meter square per unit of flux. So usefulness of this, I will solve a very simple, I'll give a simple example over this, and we'll learn how to calculate the flux over a volume. So take an example. Let's take an example. So I will take an example for which I already know the electric field. So take a Q, a point charge Q, and I will take the closed volume as a sphere, closed surface as a sphere. For some reason, we like to call it a Gaussian sphere. A Gaussian sphere. And the sphere is imaginary. Means there is no actual material here. The sphere is imaginary. All I need to know about the sphere is it has a radius r. So at the center of this sphere, there is a charge q. Now, what I will do, I know I can draw electric field lines for this. I know that it is radially outwards at each and every point on this sphere. It will be radially outwards. But if I take a small region, let us say here, call this as dA. Now dA vector will be along the radius only. The direction of dA vector will be along the radius because it is a sphere. All the points, all the small areas on the surface will be radially outwards. Let us say electric field here is E. I know that electric field at each and every point on the sphere is just 1 by 4 pi epsilon naught into q by r square at each and every point. Of course, the direction will be different. The direction will be radially outwards. Direction is radially outwards. But see, your area vector dA, that is also radially outwards. Area vector is also radially outwards. So when I calculate the flux through a closed volume, E dot dA, I can write this as just E dA cos 0 degree, because both have the same direction, the area vector as well as the electric field vector. So that is integration of E into d. I can put the value of E. The value of E is 1 by 4 pi epsilon naught into q by r square into d. I don't know the value of d. It's very small area. But see, value of q, r is a constant. Q is a constant because charge was given. R is a constant because it's a sphere. The radius cannot vary. It's a given sphere. And 1 by 4 pi epsilon naught is of course a constant. So I can write 1 by 4 pi epsilon naught into q by r square into closed integration of dA. All these things are constant. It can be taken outside the integration. Now, the closed integration of dA is basically the total area. Integration gives you the sum of all the things. If like this, you add up all the areas on the surface of this sphere, what you get? You get total area. So integration of dA is just 4 pi r square. That is the total area. What is this? Integration of dA is sum of all infinitesimal area. The sum of all infinitesimal area is the total area. That is obvious thing. Because what we don't even need mathematics. This is just representation. Integration of dA is 4 pi r square. Integration of all the small areas on the surface of the sphere is 4 pi r square. You can put that value here. It will be 1 by 4 pi epsilon naught into q by r square into 4 pi r square. This 4 pi will get cancelled, r square will get cancelled. And the final result of the flux that we get is that flux is equal to q over epsilon. This is flux due to a closed sphere. So Gauss theorem, it gives a relation between electric flux and the charge inside the Gaussian surface. So it states like this: the total flux inside a closed surface is summation of E dot ds, and this is equal to charge enclosed by epsilon. We have also discussed in the last class how to calculate flux due to a electric field due to a single charge. We have derived this formula. Now, to apply Gauss theorem, it is applicable for any closed surface. For example, if I have charges Q1, Q2, Q3 here in this region, and we have a Gaussian surface like this. In that case, if you want to write the total flux through this surface, this will be called a Gaussian surface. So total flux through this surface will be equal to Q1 plus Q2 plus Q3 divided by epsilon naught. Taking a different scenario, let us say I have my charges arranged like this. Let us say the second charge is negative. Third charge is also negative. And our Gaussian surface is arranged like this. Okay, so Gaussian surface is an enclosed volume. In this case, you will see again the flux, if you write this, you'll not worry about the charge Q3. As I said, the Gauss law says that the electric flux only depends on the charge that is inside the Gaussian surface. So we'll write this as Q1 minus Q2 whole divided by epsilon naught. Now, if you think about it, you can also write the flux as E dot ds. Now, ds is any region. No? ds is any region, suppose here. This is a small surface, ds. And let us say the electric field is E. Electric field is E vector. And this vector is your area vector. This is your area vector. So can anybody tell what is this electric field due to? There are three charges. Then what does this E signifies here? Is it the charge given by Q1, Q2, or Q3, or only Q1, Q2?
Only Q1, Q2.
Q2, Q1.
That seems to be the case, but it's not like that. This electric field here is the net electric field. This E here is the net electric field due to all the charges. Due to all the charges. I'll explain how this comes. First, let us understand what this law says. So E is here is electric field due to all the charges, or net electric field. You can write it as electric field or electric field due to all the charges. And this charge is only the enclosed charge. Now this is surprising that electric field is due to all the charges, even the charges that are outside, but it depends only on the charge inside. Now why does this happen? See, Q1, Q2, and Q3, they will give their own electric fields at this point. And we can calculate net electric field due to using principle of superposition. So my E vector at any point will be electric field due to the first charge plus electric field due to the second charge plus electric field due to the third charge. That was this law says. But see, if suppose this Q3, suppose if I draw the electric field due to Q1, if I draw the electric field due to Q1, so it will be like this. It will be directly radially outwards. And somewhere here it will cross the surface. So all the electric field lines that are given by Q1, they cross the surface. Same goes for Q2. All the electric field lines that are due to Q2, they are crossing the surface. So Q1 and Q2 have their E dot ds added up or subtracted up. If it is outwards, then E dot ds is added up. And if it is inverse, then E dot ds is subtracted. Don't worry about this. What we do here is finding the net field. This net field will be found out by adding the electric fields, considering them as vectors. But if I talk about Q3, here, now electric field due to Q3 is crossing the surface 2 times. It will cross the surface 2 times. So flux due to Q3 first enters the Gaussian surface, then exits the Gaussian surface. So flux due to Q3 first enters the Gaussian surface and then exits the Gaussian surface. Now this is the reason that electric field that we are taking is the net electric field, but the flux that we are getting, net flux, depends only on the charge that is inside the Gaussian surface. I'll explain it in other terms again. Suppose I have charge Q1 here and my Gaussian surface is drawn here. So you know that the flux, so if you calculate the flux, the charge inside is 0. So flux will be 0. For this case, the flux will be 0. Flux is 0, but at each and every point there will be electric field, right? If I draw the electric field lines due to this, it will be like this, going radially outwards. No doubt about this. You know, the electric field due to a point charge is radially away from the particle, from the charged particle. So see, at this point, if I write a ds, let us say ds is like this. This is ds vector, this is E vector. And again, here it will be another ds. So ds is, let us say like this, ds vector, and this is your E vector. So you can see if I do summation of E dot ds, at one point the flux is entering and at other point the flux is exiting. So flux is like a flow, the electric field is flowing from the positive charge to the outward direction. In that sense, the summation of E dot ds, you can see here it is 0. And that is why the electric field is the net electric field. As I said, the electric field is the net electric field due to all the charges, but flux only depends on the charge inside, because the charge outside gives no resultant flux. Charge outside will give no resultant flux. Okay. So here also, if you divide it into 3 types of fluxes, one is flux given by charge 1, then flux given by charge q, charge 2, and flux given by charge 3. So their sum is q1 minus q2 by epsilon naught. But flux given by charge q3 is 0, because electric field lines are entering then exiting the Gaussian surface. Okay, and this is my total flux. Any questions over here? Any confusion, any doubt?
Sir, could you please repeat? Actually, my internet connection is lagging. So, sir, you were saying that there are three types of fluxes and
Not three types of fluxes. There are three charges. So
charges.
flux will
Okay.
be given by each of the charge.
Hmm.
Now this flux is only exiting. So there will be a net flux. Flux due to Q1.
Okay.
Q2, the flux is only entering. So there will be a net flux. But due to Q3, flux is first entering, then exiting, because there is no net flux for it. So due to charge Q3, there is no net flux. And that is why the resultant of net flux of Q3 is 0.
Hmm.
Okay. So that's why for any charge which is outside the Gaussian surface, the net flux will be 0 here.
Okay.
Now, Gauss theorem is always valid, but only useful for symmetrical cases. Gauss theorem is always valid, but useful only for symmetrical cases. I'll tell you what it means by some examples. Gauss theorem is always valid, but only useful for finding electric field when symmetry exists. When symmetry exists. And we'll use this to find the flux due to different scenarios.